Right, I'm here to talk about the performance of the interpreter. Morten showed this slide earlier. This is what we call a performance QA report, comparing the 14.1 release of the interpreter with 14.0. The comparison is done by running, I think, 13,500 expressions lots of times over, doing lots of things to try and eliminate all the variability that you get in the timings, and then grouping them into 136 different, roughly equivalent functional groups. So, for example, plus gets one group with a whole different bunch of argument types. So they're aggregated like that. And then we plot on a graph. The graph, the scale here goes from minus 20% to plus 20%. It's designed to detect fairly small changes in performance. And every time we do one of these comparisons, it's arranged so that blue is good. We're comparing 14.1 on the left. The blue areas represent where expressions run in 14.1 were running faster than the equivalents in 14.0. So this is a very good chart. This is the kind of thing we like to see. It's almost inevitable that you get, in every comparison, some things slow down as other things speed up. So the fact that there's a small red tail there is, it's sad, but it seems to be a fact of life. What we do is try to minimize the size of that tail and try to get as much good blue stuff on the left as possible. These were originally designed to detect performance regressions where things might have slowed down by a few percent here and there, so the scale is quite compressed. It should be able to reliably detect something like a 2% change in performance. And one of the effects of that is that when clever guys like Roger go in and speed things up by a factor of 10, it's way off the top of the chart somewhere. So when you see really good algorithmic optimizations, they just appear as a big blue column here that gets truncated at the top of the slide. The thing I particularly want to talk about today is Morten mentioned that this year we've been trying to upgrade the C compilers that we use for compiling the interpreter with. This might seem like a trivial thing, but it turns out it's actually quite a difficult job to do safely. The reason why we want to do this might be obvious. We hope that the compiler vendors are putting in as much work as we are in trying to speed up the C compilers as we try and speed up the APL interpreter, so we want to take advantage of as much cutting-edge work that the compiler vendors have been doing as possible, and to a lesser extent the newer compilers have better support for bits of the C and C++ language that we'd like to use in the interpreter. The reason why it's difficult is that the compiler vendors tend to tell you that their compiler produces code that is, 2% faster, 5% faster, or whatever. And for us, that is simply not enough detail. It might be 2% faster overall on someone's application, but we're very, very careful to try not to introduce any regressions on any of the things that we're measuring. So an overall improvement is not always good enough if there are some things on the right-hand side. If there's a big red tail that is slowed down, that can be unacceptable for us. First of all, so I'm going to talk about the three main platforms that we've supported historically, which are AIX, Linux, and Windows. On AIX, we use IBM's compiler. It's called XLC. This was a fairly painless upgrade. We were upgrading from version 12.1 of their compiler, which was released 3 years ago, to version 13.1, released 1 year ago. So, relatively minor thing. The main reason for doing this upgrade is that the newer compiler can take advantage of Power 8 hardware, which I know some people are now working with. It was pretty painless. The only problems we ran into doing this were discovering some bugs in the C compiler, but luckily IBM are fairly responsive and fix those if you report them. On Linux, slightly more interesting because we're upgrading from a 6-year-old compiler, and because the compiler we use, GCC, the rate of change in GCC is very large because it's an open source project. There are hundreds of developers from a whole bunch of different companies working on it constantly, so you get a lot more sort of churn in the capabilities of the compiler. One additional reason for upgrading in this case is that compilers these days have a lot better support for what I've called SIMD instruction sets. So on Intel chips you get things like SSE and SSE2. They're instruction set extensions that let you operate on a bunch of values in parallel at the same time. I'll say a little bit more about those later. Every time we attempt a compiler upgrade, we use the performance QA to try and work out what's got better and what's got worse. And so this is the one for the GCC upgrade, upgrading from version from 2009 to one that came out, I think, last year or early this year. And generally it looks pretty good. You know, that's quite a good graph. It's slightly disappointing that there's a red spike there. In this case, obviously whenever we get regressions like that, we go and investigate and try and work out what's wrong and if there's anything we can do to sort it out. There was one group on the right-hand side here which had dropped in performance by, 13%? So up here there are things that are sped up by 20-odd%. This is drilling down into one of the things that's sped up a lot. In this case it's a group of expressions doing plus dot times, and here we have a list of all the individual expressions that use plus dot times with various different combinations of argument sizes and data types. And you can see for each individual expression that was run, this is a little histogram of how long that expression took with the newer compiler versus how long it took with the older compiler. And in the very best cases here, I don't know if you can read the numbers off the scale, but there was something like a factor of 6 improvement in that plus dot times calculation. And the reason for that is because the compiler can automatically take advantage of the vectorized instructions, which in some cases can crunch, 4 or 8 or 16 values in parallel in one instruction. At the other end of the scale, there was a little red spike on the right-hand side of the graph. This one, on investigation, turned out to be there was nothing obviously wrong with the C code. We can even drill down and look at the assembler that the compiler is generating, and again, nothing obviously wrong. It just turned into a very, very tight loop, and the instructions were very slightly different. And in some unfortunate cases, that was leading to a 30% change in performance. So at that point, we have a decision to make. Sometimes we can just tweak the C code a bit. Sometimes we just have to live with it if the overall performance of everything else is good enough. For this particular one, I think there was something that we did to the C code just to change things and get rid of it. Can't spend a lot of time investigating every single regression, but we do try. Now on to Windows. This was probably the most challenging compiler upgrade for a few reasons. One of which is that we use Visual Studio, the Microsoft compiler, and we've been using a 10-year-old version of that since before I joined the company, which was 5 years ago. So the upgrade from 10-year-old compiler to one that came out this year spans quite a lot of time. There have been quite a lot of changes in the compiler over that time. Now, remember those performance graphs where I was saying that blue is better and we want to see a lot of blue on the left-hand side? The first attempts at compiling with Visual Studio 2015 ended up like this, which was mildly disappointing. This is one of the things you encounter when you're trying to do these upgrades. So, luckily, because it's such an obvious regression, it's not too hard to work out what was going wrong. This kind of thing is not atypical at all. In this case, there are, I don't know how many of you know C, but there are some fairly core C functions called set jump and long jump, which we happen to use in a lot of the interpreter. And Microsoft, in their wisdom, had changed the way they work to make them interoperate, I think, better with C++ or .NET or something. Something that we weren't really that interested in, but we were relying heavily on the performance of them. So it affected almost everything you do with the interpreter. In this case, it's one of the few bits of the interpreter that are important enough that we can rewrite bits of it in low-level assembler. We've done that before, and doing that in this case got rid of that regression completely and gave us a graph like this, which is overall pretty positive. There is a nice blue tower here going off the top of the screen. The red tail is larger than we'd like ideally, but again, overall, not too bad. This, just for interest, is the this is the very end of the red tail, the very worst expressions over here. And in this case, the worst expressions are all doing exponentiation. Even exponentiation on an array of doubles got 50% slower. And it's hard for us to address that because the interpreter does almost nothing. It just calls to the C library, says, please exponentiate this value. And the C library has got slower in that case. We can report it to Microsoft. We've had some success with that in the past, although they're not very responsive. Or, in the worst case, we can grab some code from somewhere else to do that calculation. We had a similar thing with memset and memcopy, actually, which are more very core C functions which you use for moving data around, which are again heavily used by the interpreter. And when we were trying an upgrade to, I think it was Visual Studio 2012, it turned out that in some cases they'd slowed down by a factor of 2. That was solved by complaining to Microsoft. It's one of the things they fixed for us. Another thing that made the upgrade to Visual Studio 2015 slightly challenging was that it has compatibility issues. We've previously shipped with the .NET Framework version 2. Visual Studio 2015 has moved on to .NET Framework 4, and also Microsoft have dropped support for Windows XP. In this case, I don't think it was such a big deal, but it does mean that we will have to drop support for XP as well. I don't think that affects too many people. Now, I mentioned the fact that modern CPUs have vector instructions. Over the last 15 or 20 years, I think probably been by far the biggest change in the single core performance of the CPUs that are coming out is the fact that they're coming out with new vector instruction sets all the time. So since I'm just looking at Intel and AMD chips here, in 1997 they introduced a new instruction set called NNX, which could handle, I think, 8 bytes worth of data at a time. And since then, they've regularly come out with updates to this. So SSE and all the various different flavors of SSE can process 16 bytes of data at a time. And now they've done AVX, which does 32 bytes of data at a time, and they're even looking forward to 64 and 128 bytes of data processed in a single instruction. There are two ways you can take advantage of this. One way is that you wait for the C compiler writers to get really clever, and they can spot when you've written C code that is really just doing a bunch of operations in parallel, and they can generate code that will use the vector instructions for you. It would be wonderful if we could just rely on that in all cases, but it's still, the C compilers aren't really there. They're getting better all the time, and they can do it in some cases, but it's not good enough that you can just rely on it all the time. In case that this is a case where it's worked quite nicely, this is the plus.times in a product that we looked at before. The innermost loop for that in C code looks like this, and that is simple enough that the C compiler guys recognize that and say, I know what's going on here, and they turn it into, this is the guts of the inner loop in assembler, and the interesting thing here is that they're using instructions like this. The PD suffix on these instructions stands for parallel double, so it's multiplying or adding a bunch of double precision floats in parallel for you. So we didn't have to do anything for that. The alternative, if the C compiler isn't smart enough to do it, is that you can write the C code yourself and be explicit about exactly what instruction you want to take advantage of. So this is a page of Intel documentation where they're saying the CPU has an instruction, this is add PD, add some doubles in parallel, and you can write C code that says please use that exact instruction, so you can tell it exactly what code you want generated. This is quite a lot of effort because you have to worry about which platforms it's compatible with, and sometimes you have to check at runtime whether the computer you're running on has that particular extension. But the benefits can be worth it. In particular, for simple reductions, max reduction, min reduction, plus reduction, this is kind of the best case for the vector instructions. They read a lot of data and they do a very simple calculation on it. They don't even have to write a lot of data, they just give you back a number at the end. And the very best of the best case, we've handwritten C code using those intrinsics for max, min, and plus reduction. And if the conditions are right, for example, doing max reduction on a long vector of small integers, you can get, in the best case, something like a factor of 30 improvement over what you get with the plain C code. And that, as Roger will explain, I think, is really a game changer. That lets you do things to kind of pre-process arguments to more complicated primitives. Things that you couldn't afford to do before now become so cheap that you can use that to enable other optimizations. Most CPU families have these vector instructions. It's not just the Intel things. The IBM Power architecture has a similar thing. It's originally called AltiVec, and then they too revised it, and the second iteration was called VSX. And again, these simple reductions we've implemented for Power as well, and the speed-ups are broadly similar, factor of 20 at best. And as well as plain vector instructions, the Intel and the Power guys occasionally bring out new wacky instructions that do things like bit manipulation or anything, typically things that are used for signal processing. And in some strange niche cases we can take advantage of this. So in 14.1, I think, if you do a transpose on a square Boolean matrix, the size is a multiple of 8, it can do some really clever bit twiddling, taking advantage of an instruction that rearranges bits in a word. In that case, sped up by a factor of 10 by taking advantage of one slightly peculiar instruction. And there are other examples of bit manipulation instructions that sped up things that are taking Boolean data and expanding it out to word data, or doing the opposite, taking an array of integers or doubles and squeezing it down to a Boolean matrix in a compaction. That is all I have time for. I shall hand over to Roger.
My part actually will match quite well with what you said, Jay. So, recent and future versions of Dyalog benefited from the application of several techniques, including range finding using vector instructions, the same vector instructions that Jay mentioned, CRC hashing, special code and operators, and magic functions. So first, some acknowledgements. The Jay Foad wrote the interfaces to the vector instructions for finding min and max, and also to the CRC instruction. And John Scholes and Richard Smith did the work that made magic functions possible. And I get to talk about it. So for functions in the index of family, including iota, are faster for small range arguments. So in this example, or in this benchmark, x and y are small range, and s and t are not. And the range is relative to the size of the argument. So for iota on 4-byte integers, small range in this case is 6.5 times faster. But how does the interpreter know what arguments are small range? Well, it computes the range. And since SSE2 2001, there have been vector instructions for finding the range. And it's advantageous because using the vector instructions, the range finding takes 2% of the time for the total computation for iota. And that 2% is important because we found that we cannot reliably detect timing differences of less than 5%. So nobody can complain that because we're doing this special work to exploit small range, we're slowing down the general argument. And at the same time that I put this in, I sped up the general arguments by a factor of 4, 5, 8. So you can't really complain. And this contributed a lot to the blue mountain that you saw before. I love the blue mountain. Quite a few primitives exploit small range, including the ones you see up there, the index of family, grading and sorting, key, and of course max reduce and min reduce themselves. And last, indexing, which is a little bit surprising, but it uses the range finding to check for index bounds, check for index errors. And that's important because if you separate the index bound checking apart from the data movement, then the data movement part is completely non-branching. So we APLers have always known that non-branching code is better, faster, simpler, and it turns out that the CPUs are catching up to that. The next implementation technique is CRC hashing. CRC stands for cyclic redundancy check. It's a checksum on a stream of Boolean data. Mathematically, it's the remainder of division by a prime polynomial. Okay, so there we use the 32-bit CRC. Now, for functions in the index of family, CRCs are very useful. First of all, because the probability of CRCs being the same for unequal streams of bits is very small. And secondly, CRCs can be computed in real time, which is better than linear time. And finally, there's an instruction for computing the CRC. So, and these primitives use CRC, and the Dyalog version where they came in are indicated. Index of the extended definition, index of on inverted tables, and index of on relational matrices. A benchmark. So in this example, X is a relational matrix. So if you don't go down the columns, all the data types are the same. The lengths need not to be the same. And so in column 2 it's small integers, and in column 3 it's followed by integer scalars, and in column 1 they're character vectors. So, and Y is very similar to X, except I deliberately made it not a relational matrix by putting a character vector in this corner. So, for relational matrices, I use CRC hashing, and for non-relational nested matrices, it uses the old algorithm, and it's about 9 times faster. Now, if you convert the relational matrix X to be an inverted table, it's even faster. And the inverted table primitive, the 8 I-beam, also uses CRC. But it can do faster things because all the columns are collected together into a single simple array. So this is one character matrix, an integer vector, another integer vector. Okay. So both of these use CRC, but because T is an inverted table, it can be quite a bit faster. Now, if the machine that the program is running on doesn't have the CRC instruction, then the primitive falls back to a C-coded hash. And the next benchmark indicates the difference between the two hashes, the timing difference. There's a star because it's not really computing the same hash code. So it's a factor of 3 faster using the CRC instruction versus the C-coded hash. And I also have inverted table using the C-coded hash, and it's faster by a factor of 2. So the next technique are special code for operators. Now, operators like the key operator have potentially an infinite number of cases, but only a very few of them are useful. So the strategy is to provide special code for those useful special cases. So for the key operator, these are the special code. A couple ones are not there yet, but they'll be added. And additional special cases can be implemented as required. So much for special code for the key operator. What about the general case of the key operator? The answer is magic functions. So this is the what is a magic function? A magic function is an APL-coded computation in the C source of the interpreter. In particular, it's defun. And by that, I include D operators. So this is a D operator that implements the key primitive. And now magic functions have been used since the 1970s in the mainframe APL interpreters. And its magic functions have been used since day one in J. And they have been used in Dyalog since about 1.5 years ago. And the fact that defuns are magic functions are defun makes a significant difference in Dyalog compared to other magic functions. And I want to say this carefully. Interpreter performance work has been informed by what's used in the magic functions. So the stuff in red are speedups we have done since the implementation of the key operator. So implementers don't fight fair. You know, never get into a benchmark fight with an implementer. So it's instructive to see what happens if we replace some, if we use magic operators or magic functions for existing operators. For example, the dot operator has this magic function. Pretty cool, huh? Rank. And do a timing. Now this is the primitive plus dot times. As Jay mentioned before, it has been highly optimized by hand in C, and also because I did this benchmark in Visual Studio 2012, it has the vector, the compiler can do the vector instruction thing. So it's not surprising that it's 271 times faster than my magic function. But then we notice that the right operand function omega is applied through the each operator, and I know that each doesn't make a special case for scalar functions. Okay. So what happens if I make a different version of the magic function? Oh, okay, so this is a previous benchmark, and I removed the each and named it .0. Now it's only 8 times slower than the highly optimized plus dot times. So that's not bad for 5 minutes worth of analysis and coding. And here's the pièce de résistance. If I use general arguments that the primitive dot operator doesn't recognize, to the same, and the same thing for the magic function, the magic function is faster. Any questions for me or for Jay?
This one's for Jay, and it's about your changing C compilers, or related to it anyway. As Roger's comment about, oh, and if your target machine does not have this instruction, we do something. I like the CRC, we do this. It occurs to me that a simple to me way of dealing with people who, let me back up. You've got to pick an architecture and have people choose and implement to that architecture. And when someone comes out with a new flavor that has 2048-bit vectors, you don't have any support for it. And you have no way to do that except by going in and making the decision to release a new version that may not support the old ones, and so on and so on. A simple way around that is to have a bunch of binaries that you ship all at once. Say, well, this one supports AMD boxes with 256-bit vector ops. This one supports Intel with 512, and so on. And then you pick one of those binaries at the time you start the Dyalog interpreter. And this would give you all that capability on the fly, as well as giving the ability to upgrade to support those new the new flavors of hardware immediately without having to wait for a new release.
Yeah, I see that as a trade-off between making our life a bit easier as C programmers because we wouldn't have to implement all the runtime checks for what instructions are supported, versus making it more complicated for the people who package and distribute the application. And at the moment, yeah, that's true. At the moment, the runtime cost of doing the dynamic checks for what instructions are supported doesn't seem to have been a problem. So it hasn't forced the issue. I mean, I agree in theory in some ways it would be better to build different interpreters, but it does make the packaging more complicated and it makes the QAing process more complicated in some ways. So we haven't done it yet. I'm not sure if we'll go that way or not. Okay?
Thank you.